Hello kids. Today we want to discuss the logarithmic function and its graph. What I want to do is start with a little argument as why we need to have the logarithmic function and why we study it in Algebra 2. And then after that we'll move on with the graph of this function and some of its characteristics. So let's begin with why we study logarithmic functions in Algebra 2 to begin with. So I'm going to start out with a cubic equation like x cubed is equal to 64. X cubed is equal to 64. Well, how do we solve this? We really don't need any algebraic methods to solve this equation. We can use mental math and ask ourselves, what number to the power of 3 is 64? Well, we know that 4 to the power of 3 is 64, therefore x is equal to 4. This is called mental math, and no algebraic methods are needed. Likewise, if I write down an exponential equation like 2 to the power of x is equal to 8, I don't need any algebraic methods for this because I know 2 cubed, 2 to the power of 3 is 8, which means x is equal to 3. Again, this is called mental math. But sometimes mental math doesn't work. For example, if I had, back in my cubic equations, if I had x cubed is equal to 10, well, I don't know what number raised to the power of 3 is 10. So for this, mental math is not going to work. So we turn into an algebraic method. In algebra, in order to isolate the x and solve x, we have to do the inverse operation. In this case, the inverse operation that's required is the inverse function cube root of x. And so I'll take the cube root of each side. Now, the cube root function is the inverse function of x cubed. So the cube root of x cubed is just x, and I'll know x is the cube root of 10. So in order to isolate the x, I needed the inverse function for a cubic. Likewise, if I have an exponential function, exponential equation, let's say 2 to the power of x is equal to 10, I don't know what power of 2 is 10, so I need the inverse function for an exponential. Well, it turns out the inverse function for an exponential is the logarithmic function. So if I know logarithmic functions, I can isolate x and say what the value of x is, which at this point I don't know. Now, logarithms were invented at the beginning of 17th century, not for this reason. Logarithms were invented to make numbers smaller and manageable, and for arithmetic operations to become simpler. So if you had a sophisticated, tough equation, or not equation necessarily, some arithmetic operation, and it was complex, you would use logarithmics to make it simpler. With the use of logarithmic properties, you can bring down a sophisticated operation into just adding and subtracting. In fact, the country I'm from, Iran, before the widespread of the use of calculators, all math students carried with them a log table. So my brothers, myself when I was younger, my dad, they all walked into their math classes with a log table. And in our Algebra 2 classes, I have showed you this log table, and we have used it before. But so that was the reason for the invention of logarithms. But in our Algebra 2 class, we use logarithms as an inverse of an exponential function in order to solve exponential equations. That's our biggest need for it in Algebra 2. So I want to start by constructing the graph of a logarithmic function with the idea that I know that the graph of an inverse of a function is the reflection of the function's graph over the line y is equal to x. So this dashed line is the line y is equal to x, and I've graphed the function y is equal to 2 to the power of x, which you had to in your exponential worksheet. I've graphed it. I've used 1, 2, 3, 4, 5 points, and I connected these points, and we've already talked about the characteristics of an exponential curve, which what this is called. But now I want to use this exponential curve reflected over the line y is equal to x and get the graph of its inverse, which we're going to name or we're going to call the logarithmic function. So how do we reflect the graph over the line y is equal to x? Well, we'll take each of these points and switch the x and y coordinates and find the image of these points and then connect them and we get the graph. So for example, I'm going to start with the y-intercept 0, 1. That becomes an x-intercept 1, 0. The point 1, 2 becomes 2, 1. When I switch the x and y coordinates, the point 2, 4 becomes 4, 2, 4, 2. And on I go with the other 2 points. Negative 1, 1/2 becomes 1/2 negative 1. And negative 2, 1/4 becomes 1/4 negative 2. And then I'll connect these points. I'll do the best I can in connecting this. And as you can see, as the exponential curve goes higher and higher, the logarithmic curve also goes higher and higher, but at a much slower rate. Exponential curve just shoots up. As x goes to the right, the rate of growth just increases and it just shoots up really fast. In fact, in the English language, when we talk about something that grows fast, we say, oh, it's growing exponentially. Well, the logarithmic curve also increases, but the rate becomes slower and slower as we go to the right. We'll go back and talk about this when we reach the slope part of our worksheet. For now, a couple of observations. If we had a y-intercept for the exponential curve, we have now an x-intercept for the logarithmic curve. That x-intercept is 1, 0. If we had a horizontal asymptote, meaning that the curve gets closer and closer to the x-axis, this horizontal line, which we call a horizontal asymptote, for the logarithmic curve, we have a vertical asymptote, the y-axis. As we get closer to 0, this curve gets closer and closer to this line x is equal to 0. So we call that a vertical asymptote, right? I wish I had done a little better job with this graph, but unfortunately this is the best that came out, but that's fine. We're going to call this function, this logarithmic function, log base 2 of x. And notice this subscript 2 is our growth factor 2 from up here, right? And for short, we say log instead of spelling out logarithmic. So this is our inverse function to the function y is equal to 2 to the power of x. As we move on, we'll talk about the domain and range of the logarithmic function, and we can kind of see what the domain and range is by looking at the graph, right, you can see that the graph only exists to the right of the y-axis, never touches the y-axis, so we're going to say that the domain is a set of positive reals. But at the same time, you can see that this curve covers vertically covers all of this y-axis, so the range is the set of all real numbers. That goes in line with the idea that x and y get switched. Remember, the domain of the exponential function was all reals. Now the range of the logarithmic function is all reals. Okay, so let me move on to our worksheet, and let's see if I can help fill out some of the boxes and hopefully leave some of the boxes for you to fill out. So here is our exponential function. That's the parent function. If I may write that with a little bigger font, y is equal to log base b of x. And this b is the base or the factor that we had in our exponential function. Of course, this b has to be a positive number, not equal to 1. The example of b that I used in my graph was 2. If I were to fill out this table, I wouldn't be able to fill out, come up with the value for y when x is -2 or -1 or 0. Why is that? That's because the domain of a logarithmic function is the set of positive reals. So the domain is the set of positive reals. Now, how do you write the set of positive reals? You either write it out with words, or you use interval notation and you say from 0 to infinity. This is an open interval. Neither 0 is included, and of course, obviously, infinity can never be included, so we use parentheses. The range of an a logarithmic function, as we just said a minute ago, is the set of all real numbers. In other words, the curve covers all of x-axis. So here's actually a better curve that I drew the first time before I recorded myself. So you can see this curve covers all of the y-axis. So the range is the set of all reals. Now, how do you want to write that again? Using interval notation, you say from -infinity to infinity, or sometimes some people would just write r, which is the symbol for real numbers. The direction of the graph, both the exponential curve and the logarithmic curve, as we go from left to right, they both go up. They both rise. That means that both functions are always increasing. Now, I can say always increasing, but that comes with a little caveat. The logarithmic function is not defined for negative values of x. So when I say always increasing, it might be a little confusing to the reader. So most people might say it's always increasing on its domain. So whenever it's defined, or wherever it's defined, it's an increasing function, it being the logarithmic function. So I can either say always, or I can say always on its domain, or I can actually just say, hey, from 0 to infinity, this function increases, right? Does it ever decrease? No, it does not. Right. The exponential function had a horizontal asymptote. The logarithmic function has a vertical asymptote. The y-axis is that asymptote. Now, again, we can just write y-axis, or we can say the equation, we can write the equation of this axis, which is, which is x is equal to 0. Right, that just is the reader's and the user's preference to either say x is equal to 0 or to say the y-axis. We do have an x-intercept. Right. That's the point 1, 0. So the point 1, 0 is an x-intercept. And the logarithmic curve never intersects the y-axis, so no y-intercepts. Just like the graph of the exponential function passed the horizontal line test, meaning no matter where I put a horizontal line, there'll be only one intersection with the graph. So the exponential curve passes the horizontal line test. Now, what does that mean? That means the function is 1-to-1. Well, we can say the same thing about the exponential curve, the logarithmic curve. It passes the horizontal line test. No matter where I place a horizontal line, there only be one intersection with the graph. So yes, the logarithmic curve passes the horizontal line test, which makes it a 1-to-1 function. So the logarithmic function is 1-to-1. Now, as a consequence of being 1-to-1, the logarithmic function has an inverse. And its inverse, of course, is the exponential function. So passing the horizontal line test, the graph passing the horizontal line test means the function is 1-to-1. And if the function is 1-to-1, it means it's an invertible function. Invertible meaning it has an inverse, and in fact the inverse is the exponential function. Just like the exponential curve didn't have a highest or lowest point, the logarithmic curve doesn't either. But the argument is a little simpler for the logarithmic curve. It's really easy to see that no highest and no lowest. On this end, it tends to negative infinity. On that end, it tends to positive infinity. It keeps going up. So it's really easy to see that. For the exponential, it was a little harder to see that there is no minimum, because you might want to say, oh, the minimum value maybe is 0, but really isn't, because the curve never actually touches or intersects the x-axis. So it gets smaller and smaller and smaller, but it just doesn't ever touch it. So no, there is no minimum here. There is no lowest point here. Well, no highest point and no lowest point means the function, the logarithmic function, does not have a maximum or minimum values. As far as slope is concerned, the only function that has a slope is a linear function. Its graph has a slope. The rate of change is constant, and we call that constant rate of change the slope of a line. And neither one of these two curves have a slope, but there can be a discussion about the rate of growth of both these two. Remember, both of them are increasing functions. Both curves are rising curves. So the discussion is not what's the slope, but is the rate of change, is the rate of growth increasing as x gets bigger? Well, in the case of the exponential curve, if I use steepness as a way of describing how it grows, notice that if I'm at x is equal to 0, this is the steepness of the curve, kind of. But as I move on, let's say when x is 1, the steepness of the curve increases, and at x is equal to 2, it gets really steep. In fact, the exponential curve, as you go to the right, the steepness increases. In other words, the function grows faster as x gets bigger. Not only the function gets bigger, but the rate at which it gets bigger gets bigger. On the other hand, the logarithmic curve is not like that. It's the exact opposite. Even though the graph is rising, the rate in which is rising slows down. Notice let's say at x is equal to 1, this is kind of what the steepness looks like. But when we move on to x is equal to 4, this is the steepness of the graph. Right? So not only the function does increase as x gets bigger, but the rate of increase slows down. Right? So no slope, but there can definitely be a discussion on the steepness of the curve. There isn't any kind of symmetry with respect to either the x-axis, y-axis, or any kind of point symmetry. The end behavior is interesting, right? The right end behavior is obvious. In other words, as x approaches infinity, I can clearly see that y, this is y, the height of the curve. The height of the curve as x gets bigger, the height of the curve gets bigger too. So y tends to infinity. So that's pretty clear. What's not that straightforward is talking about left-end behavior. Or first of all, there is no left-end behavior. The graph doesn't even exist on the left side of the x-axis. So there is no left-end behavior. So the logarithmic function does not have a left-end behavior. But we can still look at the left side of the graph. Here's the left side of the graph. Notice the left side of the graph is going toward negative infinity, right? But what's x doing as the graph is going down? Well, x is getting closer to 0. So we don't have a left-end behavior, but we can say as x approaches 0, f of xy approaches negative infinity. The only problem with this notation is that when we say x is approaching 0, the reader, the audience, doesn't know if we're approaching 0 from the right side or if we're approaching 0 from the left side. So we have to, using notation, we have to tell the audience, hey, we mean we're approaching 0 from the right side. Well, the notation for that is to put a superscript plus after the 0. So now this is read as x approaches 0 from the right side. That's not positive side, that's just the right side. So as x approaches 0 from the right side, y approaches negative infinity. In other words, as x gets smaller, going towards 0, like 0.1, 0.01, 0.001, the value of the logarithmic function gets bigger and bigger and bigger, of course, with a negative sign. So the magnitude gets bigger, but the value gets the smaller, right? It has a negative sign in front of it. All right, kids. This is the end of our little discussion on logarithmic functions and its graph, or basically the graph we talked about most. In the next video, I will talk about a couple of transformations applied to this parent function and see what the graph looks like and what the transformations are like. Until then, take care and study hard and do your homework. All right, kids, take care.